Okay, we're at the point now where we finally know enough that we can talk about what happens in a chemical reaction. Okay, we actually know enough about the pieces that we can talk about what happens when you mix chemicals. So we need to talk about chemical reactions the way chemists talk about chemical reactions. Okay. So chemical reactions have two parts. And what divides the two parts is time, before and after. What divides them is time. So we got the stuff we start with, and then it changes into new stuff afterward. So the reactants are the things you start with. The stuff you start with is the reactants. The stuff that does the reacting is the reactant. And the thing that you make, the things that you produce, it's called a product. So in big general terms, what happens in a reaction is reactants turn into products. It's time. That's what divides it. Before and after. Okay, so chemists are lazy. They want to shorten this sentence. They shorten it by putting in an arrow. That's how a chemist would write that reactants turn into products. That arrow is a verb. It's the action word. It turns into, become. The scientific word for that is yield. So reactants yield. Yield like make, like farmers think of yield. A farmer talks about yield, they talk about how much corn they get. Okay? Yield means to make. Okay? The arrow always points to the right. So reactants are always on the left and products are always on the right. The arrow always points the same way, so we don't get confused. Okay? So it always points to the right. So what really happens in a chemical reaction? Well, Dalton already told us. As part of Dalton's atomic theory. He said every element was made up of little tiny pieces called atoms. The atoms of each element were identical to each other, and the atoms from different elements were different. And then he said a chemical reaction is. What happens to atoms in a chemical reaction? Well, they get new partners. The way they're joined to each other changes. The atoms are rearranged. Starts off with one partner, ends up with a different partner. What doesn't change is the total number of atoms. Atoms can't be created or destroyed because matter can't be created or destroyed. Okay. So our goal as a chemist is to be able to describe reactions for other people. And they describe it several ways. When you're going to describe how something reacts, you can do it in several ways. Sorry. Oh, it works. One of the ways is in a sentence. Here's a sentence that describes a chemical change. Copper, an orange metal, reacts with chlorine, a greenish yellow gas, to make copper 2 chloride, which is a green powder, a green solid. So in my sentence, I start off with copper and chlorine. Those are my reactants. And I end up with copper 2 chloride. That's my product. Okay? So to shorten that sentence, they make a word equation. And a word equation is the names of the chemicals with some symbols attached. Copper plus chlorine makes copper 2 chloride. It's got a plus sign, but it's not math. It's English. We already said the arrow is the verb. Copper and chlorine turn into copper 2 chloride. The arrow is the verb. It's the action word. That's where the action happens. The plus sign is just the word and. It's a conjunction. We're going to work through all the parts of speech, aren't we? Conjunction, junction, how's that function? Hooking up words and phrases and clauses. So we got some symbols. We've seen a couple of them already. I got out of your book in table 11.1. That's where they come from. You'll see it as you read. As you read Reading Guide 11.1, you will see these symbols. The arrow separates reactants from products. It's the verb. I always read it as reacts to form. You do it turns into, becomes, makes. Scientific word for that is yields. So there, and it's our verb. And we already said the plus sign was the word and. There's our conjunction. Our nouns are going to be the chemicals. Either their name or their formula, they're still nouns. They're things, right? We can modify those nouns by describing them a little bit. And those words are adjectives. So here's the adjectives we're going to use. If I put S, a little lowercase s in parentheses after the formula, that tells me that that stuff is a solid. Make sense? If I put a G in parentheses after the formula, that tells me it's a gas. No, at the temperature of that reaction. So when that reaction happens, it's a gas. Because we're trying to describe what we see happen. Does that make sense? So if it's a gas when we start it, we'll put a G there, or it could be a gas when we're done, which bubbles show up. Okay? Anybody know what the next line says? Take a shot in the dark? L for liquid, yeah. Aren't you glad they went with the obvious ones? That's an L, that's not an I. It's a lowercase L. And you would think that was all the possibilities. No. What about plasma, the most common state of matter in the world, or the universe? Plasmas don't react because plasmas have already lost their electrons, so they can't react. So I won't be able to do those. But say, that must be it. No. Actually, the most common one is not listed here. Most common state we deal with as chemists is not listed. Say, what do you mean? Because the most common way chemists use with it is most often it is dissolved in water. And the way you say dissolved in water is AQ in parentheses. And that AQ stands for aqueous. Aqua, water. Agua, water. Same root word. Aqua, agua. So they got the AQ for aqueous. So that means it's dissolved in water. Say, well, isn't that a liquid? No, that's different. How do I turn a solid into a liquid? I melt it. And to melt it, I apply heat, right? I give it heat and it melts. Okay? When I put salt into water, am I melting it? So that's not melting, is it? That's dissolving. So for me, something that makes these symbols make sense is the end of the Wizard of Oz. Say, what? At the end of the Wizard of Oz, the Wicked Witch says, as she dies in a puddle, I'm melting! Right? That's what she says. A chemist would write that as Wicked Witch solid goes to Wicked Witch liquid. That's I'm melting. But she was a witch, not a scientist. Because did they apply heat to her? They did not apply heat to her. She was not melting. What did they do? They threw water at her, right? So it was really Wicked Witch solid goes to Wicked Witch aqueous. I'm dissolving. She was doing what salt did, dissolve. She wasn't doing what wax does, melt. Right? See the difference between aqueous and liquid. They're not the same thing. Aqueous, okay? And most reactions happen in water because water tears it apart into pieces so the pieces can touch each other. Okay, so another way that I can indicate a gas is by putting an upward arrow after the product. It can only be on the product side. And that has to do with this aqueous thing. Because if I have an aqueous solution and I make a gas, that means I'm going to make a gas in the middle of that aqueous solution. And the way what that's going to look like is bubbles. You see bubbles form. You're making a gas in the middle of that aqueous solution, so you see bubbles form in the water. And those bubbles are going to rise. That's why they use an upward arrow. I'm going to make bubbles that rise and leave. That's why it's only on the product side, because they're trying to describe what happens. I make bubbles and they leave. Okay? A downward arrow used after a product tells you it's a solid. And again, it's about this aqueous solution thing. If I make a solid in the middle of my aqueous solution, I make something that doesn't dissolve in the middle of my water. That stuff that doesn't dissolve is going to sink down to the bottom of the container. That's why they use a downward arrow. They'll tell you which way it's going to move. The solid will sink to the bottom, downward arrow. The bubbles rise to the top, upward arrow. That's why they're using arrows as our adjectives. Okay, so those are the adjectives we need to learn about. Okay, now we need to modify our arrow. We need to modify our verb. Okay. One of the ways they modify the verb, well, come on, do what you're supposed to do. Where's my mouse? There. Okay. What is going on in the background? Okay. One way they modify is, it's hard to see what they did here. What they did is they took the arrow and cut it in half the long way and turned the bottom around. Does that make sense? I don't know what this thing's doing. Suddenly they decided it was just going to run on its own. See what's using up all my time. Who's working my stuff? So if you take that arrow, split it in half the long way, and turn the bottom around, that tells you the reaction can go both directions. Sometimes it goes one way, sometimes it goes the other. It is reversible. The reaction we're talking about is the kind of thing that happens in a rechargeable battery. Because whatever happens in the rechargeable battery has to be able to go both directions. It's got to go one direction when you're putting energy in to charge it, and it's got to go the other direction to give you the energy back. That's what we're talking about by a reversible reaction. It can go both directions. So it makes sense to write the arrow that goes both directions. We'll study more on reversible reactions later. Sometimes they will put a triangle on top of the arrow. Sometimes they'll write the word heat. Either one of those is telling you that for this reaction to happen, you have to apply heat. And if you stop applying heat, it's going to stop happening. So you have to bring outside energy into what's happening. So kind of reaction we're talking about here is what happens when you cook a steak. You turn off the heat, the steak stops cooking. You turn the heat back on, it cooks some more, right? So as long as you're applying heat, it cooks. We're not talking about lighting a stove, right? Lighting a fire. You apply heat at the beginning of lighting a fire, but then you can take your heat away. It makes its own. So that wouldn't get the heat on top of the arrow because you don't have to keep supplying it. Make sense? Okay. And the last thing they could do is they can write the formula or the name of a chemical on top of the arrow.